Why array operations matter? Array operations are not a background optimization quietly supporting Python systems. They are the invisible engine driving performance, scalability, and trust. Every data pipeline, every analytics engine, every machine learning workflow eventually reduces to arrays transforming into insight. When these transformations are designed well, systems feel effortless, responsive, and reliable. When they are not, no amount of infrastructure can compensate. Pause for a moment and consider this. Most performance problems blamed on Python are not Python problems at all. They are array problems, waiting to be understood. In real production environments, arrays are not just collections of numbers. They are living representations of the business itself. They capture customer journeys evolving over time, sensor signals streaming from machines, financial states shifting with every transaction, and models learning from millions of observations simultaneously. Every filter, adjustment, normalization, and merge is an array operation at its core. Teams that embrace this reality design systems that scale naturally and remain stable under pressure. Teams that ignore it often fight complexity they never needed, adding infrastructure instead of understanding data. Performance ceilings rarely come from weak algorithms. They emerge from how data is laid out, how memory is touched, how types silently change, and how Python loops creep into places they should never exist. Across enterprises, we repeatedly see analytics jobs consuming excessive compute, ML pipelines slowing under load, and dashboards drifting from real time. Not because the business logic is complex, but because array operations were never treated as first-class design decisions. This is exactly where experienced engineering partners like Thunabit create impact, by redesigning numerical workflows at the foundation, not masking symptoms with surface-level optimizations. This guide is deliberately not academic. It reflects how NumPy arrays behave inside real systems, where correctness, maintainability, and performance must coexist under real pressure. The goal is not to explain what NumPy is, but to show how array operations should be executed when systems must survive scale, real data, and real consequences. This is NumPy as it exists in production environments, not in isolation, not in theory. The NumPy ND array is best understood not as a container, but as a machine engineered for speed. Its contiguous memory layout allows data to flow predictably through the CPU cache, while strides define how that flow is navigated without Python touching each element. Instead of stepping through values one by one, NumPy jumps through memory with precision, applying optimized native instructions across entire datasets. Once you see ND array as an operational structure rather than a data holder, your approach to numerical design fundamentally changes. Many production bugs are not mathematical errors, they are structural misunderstandings. A row mistaken for a column, a dimension added without intent, a data type chosen for convenience instead of precision. In financial systems, this causes silent rounding errors. In scientific systems, it corrupts conclusions. In enterprise analytics, it leads to decisions built on flawed numbers. Shape, dimensions, and data types are not technical details. They are part of the system's contract with reality. One of the most damaging assumptions teams make is treating NumPy arrays like Python lists. Lists are flexible but slow. Arrays are intentional and fast. Mixing types, relying on implicit conversions, or iterating element by element quietly destroys the advantages NumPy provides. We've seen pipelines silently upcast data, lose precision, and drift over time simply because array behavior was misunderstood. Correcting this mindset is often the first step Thunabit takes when stabilizing mission-critical systems. Array creation is not a setup step, it is a commitment. Choices made here echo through performance, memory usage, and numerical correctness for the lifetime of a system. Explicit data types, deliberate initialization, and thoughtful memory allocation separate experimental scripts from production-grade engineering. Mature Python teams treat array creation as system design, not convenience, and that discipline consistently pays dividends at scale. Some of the most dangerous numerical bugs never crash systems. They quietly distort results, day after day, until trust erodes. Financial forecasts skewed by uninitialized memory, analytics reports polluted by residual values, models trained on data that was never meant to exist. These are not edge cases. They are production realities. and they demand experience, vigilance, and deep understanding of array behavior. This is where NumPy truly shines. Arithmetic applied across entire datasets. Transformations expressed as intent, not control flow. Element-wise operations convert mathematical ideas directly into efficient computation, eliminating noise while amplifying clarity. Code becomes shorter, faster, and easier to reason about, and performance scales naturally with data size, not code complexity. This is where Python finally feels fast. Beneath most NumPy operations live universal functions, ufuncs, highly optimized routines running in native code. They bypass Python's interpreter entirely, applying transformations at machine speed. This is why vectorized logic consistently outperforms loops, and why NumPy remains foundational even as higher-level tools evolve. Understanding ufuncs means understanding where real performance actually comes from. Mastering array operations is not about clever code. It's about building systems that remain fast, correct, and explainable as they grow. Organizations that invest in this foundation outperform those chasing surface-level optimizations. They trust their numbers, scale with confidence, and move faster without breaking things. If your systems depend on analytics, numerical computation, or machine learning, Thunibit is ready to help you audit, optimize, and future-proof your NumPy workflows. Because great systems are not accelerated by chance, they are engineered, one array operation at a time. High-performance Python isn't about hacks. It's about understanding how data moves, transforms, and settles into meaning. Every insight, every metric begins as arrays. Small choices in how arrays are created, combined, or accessed ripple through entire systems, affecting speed, accuracy, and reliability. Performance ceilings rarely come from Python itself. They come from how array operations are designed. Mastering NumPy arrays, understanding shape, d-type, and memory layout unlocks execution paths that are fast, predictable, and scalable. Teams that think in arrays don't just write code. They engineer systems that scale gracefully and remain trustworthy under pressure. The good news? Expertise is achievable. With intent-driven array operations, your workflows become expressive, safe, and high-performing. At Thunibit, we help organizations transform numerical pipelines into production-grade systems built to last, ensuring that data works for you and not the other way around.